I'm Chris Sbarra. I work at HRP Associates, and I will be going through how to develop cross-sections from boring logs and how to use cross-sections for environmental site characterizations.
So on this first slide, I wanted to show an example of a recent cross-section that we made for one of the state Superfund sites under the DEC contract. This is a site called Ricketts, former dry cleaner. It's in Ballston Spa, New York, a little bit north of the Clifton Park office. And just to show an example of how the surface topography, the subsurface geology, and different sample locations and features are depicted as an example of a recently made cross-section from one of our more complicated sites. So as an outline for this presentation, the whole point is to understand cross-sections, remedial site investigations, their use, but also what information we need to collect that will allow us to make a meaningful cross-section that will be useful for the investigation. So a good place to start is the collection of soil borings and logging the soils, both with observations and a PID. Once you have individual boring logs, you then assemble them into combinations of how the lithology changes throughout the site based on different locations, and your boring locations are going to be based on what information you need to complete your conceptual site model. Once you have all of your soil borings, then we can move into using them to develop cross-sections, and the purpose of how we're going to use the cross-section to further the understanding of the site, contaminant transport, and any other factors that are important to the investigation. And we're going to end on some good and one bad example of cross-sections that have been used on sites that we've either made ourselves or are continuing the investigation after a previous consultant. So this is an example of a soil boring log. This was collected by John Gorman. Basically, the boring log helps us organize our thoughts and observations when we collect a soil sample, usually using a geoprobe with direct push. And what's important when developing these soil borings is to write down what you're seeing. Especially when you're starting this site investigation, you won't know what the important information is going to be. So at least at the beginning, for the first couple of borings, it's a good idea to write down as much detail and as much information about any odors, what the different sediment types are, if you notice any significant transitions from one type of sediment to another, specifically a clay to sand to gravel transition. These are all potentially valuable pieces of information, and as you move through the site and collect more and more samples, you'll be able to see commonalities and patterns between the locations, and in your mind you can start to put together a rough idea of what you think the subsurface is composed of. The other important information is the depth to water that you see when you install the soil borings. Did you intercept the groundwater table? Did you hit refusal? Do you think refusal is just something that the geoprobe couldn't get through, or is it actually bedrock? These are all really important pieces of information when we get back from the field and we're trying to develop a holistic conceptual site model for contaminant fate and transport.
I think one thing to build on that, Chris, when you are doing your soil logging, you should be making notes in addition to the description. If it is the same material that you see in SB1, if you see it in, again in SB3, make that note so you can start putting those units together and kind of building that conceptual site model in your head as you're going.
Yeah, and it's a very common practice to, after you've gone through, let's say 5 or 6 different borings, to go back into your notes for the borings you've already completed and to see if you are maybe a little bit inconsistent with your descriptions. Because you always want to make sure that what you call the silt is very specific and doesn't change throughout the investigation, because different sediment types have different permeabilities and different porosities and allow contaminant transport in different ways. So consistency in your descriptions is going to be very important. Now you've collected your soil boring log, and now you can turn it into a visual description of what the different layers of your boring were using the appropriate symbols. So on this one, this is an example of a soil boring from a random site where you can see that the top few feet are composed of gravel, which is underlaid by silts and fine sands, transitions to clay, and then more poorly graded sands beneath that. And so you'll see as we develop the cross-sections for the boring logs, all the cross-section is just an assemblage of multiple boring logs, specifically along one particular path on the site. The purpose of a cross-section is really to answer a specific question about the nature of the site. You don't just want to go into a project and generate cross-sections needlessly, because they do take some time, and you should use them as a tool to answer specific questions that you need to know to further the site investigation. So specifically, the fate and transport of contaminants in the subsurface in both soil and groundwater are usually critical to the investigation. If there are any surface water or groundwater interactions, are we seeing surface water ponding? Are we seeing anything that would be similar to a groundwater seep, where groundwater is being expressed at the surface? Do we notice any potential subsurface pathways? That could be the higher permeability material around underground utility lines. It could be stratified drift from complex geological settings, typically found in glacial environments like till, where you can have preferential pathways within the material. And it's also a good way to evaluate how these impacts could potentially impact the receptors, whether that be wildlife or residents in the surrounding area. I've broken down the general steps to make a cross-section down to what I think are the fundamental building blocks of making a cross-section from start to finish. So the first step is to select a topographic profile, and I'll show an example of how you can generate a topographic profile with a few different software packages, or you can even do it by hand. Once you have your topographic profile set, you want to put the locations of your samples and soil borings along that line. Then you'll add the lithologic information from each boring log onto your line of section, and then you'll connect those boring logs together, and that will assemble your cross-section for your area of interest on the site. First step is based on your samples and your contaminant distribution and observations while you are doing your sampling. You want to select a topographic profile or a line of section that your cross-section is going to represent. So I have a quick animation of, for this particular site, we decided to make two topographic profiles. One going with groundwater flow direction, basically across the long direction of the dissolve phase groundwater plume, and another one going almost perpendicular to it to see if there was any structures that the one line of section wouldn't have captured. So this is an example of a topographic profile. In this example, you can see my line of section starts on one side of this mountain and ends on the other side of the mountain past a stream and a major road. And then our graphical representation of this is the elevations plotted against distance from the beginning of your line to the end. And so you can see that my line is the same length as my section. And this shows how topography changes throughout this line, shows where the mountain is, shows where the ravine, where the water is going to flow, and then off into the flat plain past the mountain. This is also a good time to introduce an idea of a vertical exaggeration, and you want a useful degree of vertical exaggeration to show the important details without over exaggerating how the topography changes over your profile. So in this example, we have a 5:1 vertical exaggeration, where for every inch in the vertical on this line is approximately 400 feet, and then for every inch on the horizontal is approximately 2,000 feet. So this allows you to see more detail than what you would see if this was a 1:1 line of section, and I have an example on the next slide that shows that. For sources of elevation data, you can either go to Google Earth. If you draw a straight line path on the surface of Google Earth and turn terrain on, usually terrain option is in the bottom left-hand corner of the screen, you can generate a topographic profile based on the elevation data that Google Earth currently has. The one thing I will caution is that Google Earth's topographic profile does not seem to filter out vegetation or buildings. So you might have some positive topographic features that are not really representative of the ground surface, but of features on the ground surface. This example was using the ArcGIS online profile tool. This one seems to use a different elevation data set than Google Earth and does seem to take into account surface features and kind of eliminates them from this. So this is a more accurate representation of what the surface topography would look like across this line of section. You can also do this by hand using a scaled topographic USGS map. Draw a straight line with a ruler and note where all of your lines of topography cross that line or intersect that line, and then you can plot that on a piece of graph paper, and that would also generate your profile. You can also request a topographic profile through the drafting log on Hike.
And I think, Chris, one other source, depending on where you are in the project, when you're doing your cross-section, we may have a survey that's done at the site, and we could get the elevations of the points off the survey also.
Yes, and that can be really helpful if you're in a remote area and there isn't good digital coverage on these publicly available services, specifically Western New York and Northern New York. Sometimes the resolution of the data is too coarse to be useful for something like this, so that's when a site survey is very important. So I wanted to show you the examples between an unuseful or non-useful vertical exaggeration of a 1-to-1 and then a 10-to-1 for, in this setting, does have some utility. So the top example is a 1-to-1 vertical exaggeration, meaning that for every inch you travel vertically, you travel the same distance horizontally. And as you can see, you really, at this exaggeration or lack of exaggeration, you have a hard time seeing the surface features because the Earth is, at least for our investigations, always going to be much longer in distance than it is going to be deep. Typically, we go to a depth of 20, maybe 30 feet below surface, but you could have a line of section that's 500 to 600 feet long. So you need to adjust the ratio of how it's represented to show the surface features in enough detail for it to be useful. Below this is a 10-to-1 vertical exaggeration. This is a pretty long section. This is it's 2,500 meters long, and your vertical values only vary by 150 meters. So in this case, a 10-to-1 vertical exaggeration gives you good resolution so you can see how the features of the surface change. So this is kind of the first step once you have your topographic profile. So we've plotted the topographic profile. This is for this line of section, this red line that crosses the street. This is a fictitious location, just in a random place, just for example purposes. So once you have your line of section representing how the surface topography changes from point A to point B, you then want to put your sample locations where they would land on this line, and then the final depth of how deep the soil boring went to. And that's represented by these vertical black lines. Once you have your sample locations and your sample depths, you can then take your boring logs and make visual representations of the lithology in place within the line of section. And so this allows you to start to see how these layers interact with each other over this distance. And several geologic laws, the law of horizontality, where sediment will probably be deposited in flat horizontal layers. Also, laterally continuous layers, meaning that these deposits are large, and so you expect to see similar sediments within a short distance from each other in your site investigations if there isn't a tremendous amount of heterogeneity. This can sometimes not be the case if you're crossing significant features. So if you start your line of section on one side of a river and go to the other side, you'll probably see a transition from land deposits to river deposits back to land deposits, but it should make some sense from one side of your line of section to the other. The other important idea to keep in mind is how far can a boring be from your line of section to still give you a meaningful result. So in this case, the boring that's furthest from your straight topographic profile line was MW24 down here, and it's still within approximately 25 feet of your line of section. You don't want to use borings typically that are hundreds of feet from your line of section, because the subsurface variability might mean that you have an accurate boring log in that location, but that boring log really doesn't do a good job of representing what the subsurface conditions are along your line. So you want to be as close to your line of section as possible for the best possible approximation of what the subsurface structure is. So then the next step, once you have your boring logs plotted on your line of section, you then, I like using a pencil and just going through and connecting my layers in a way that's simple and makes sense. What you don't want to do is try to overcomplicate your line of section. If you have multiple layers and you're not sure where things go, it's better to be conservative when you're connecting the layers from one boring to another than try to make many layers that are disconnected and don't show a realistic geologic representation of the subsurface. And for this one, I want to point out now, before we show the final version of this cross-section, that we have sand, silt, clay, and gravel in the first three borings, although the clay does get thinner as you go from MW22 to MW19. Clay was not observed in MW20. And so there's a technique called the pinch out that you can use where you pick an arbitrary distance between the boring that last had the layer and the boring that no longer does. And you basically just assume the middle between the two and that's where your clay basically runs out. I don't have any data to prove that the clay finishes here, but it's a reasonable approximation with the data that we have. And so this is the digitized final version of this particular cross-section. For this line of section, I don't have any data below these depths, so I've dashed the contact between the bottom of each boring and whatever material is below that. I don't want to make any assumptions because there could be a significant geologic feature that would be important, and I wouldn't want to make an assumption on no data. This also shows what I was describing before with the clay pinch out between the two borings, and I've picked an arbitrary place between the two borings to finish where the clay is in my line of section. And that's really the process of generating a cross section. I picked a simple example on purpose, just so you can see how the layers interact with each other and how the thicknesses can vary, but the layers for the most part are continuous across your line of section. They can be very complicated though, and I'm going to go into some examples with sites that had either complex subsurface geology or complex fate and transport of contaminants, and the cross section was a very useful tool in understanding why we were getting the analytical results that we were. So this is the first real-world example. We're back at the Ricketts former dry cleaner site in Ballston Spa, New York. But this is the perpendicular line of section to the example that we showed at the beginning of the presentation. The purpose of this cross-section, more than anything, was to explain two observations that we observed while we were sampling on the site. The first being we saw surface water ponding and pooling and appear to come out of the subsurface or come out of the ground throughout the site. We called these groundwater seeps, and we wanted to know if the groundwater was intercepting the surface or if this was caused by some other feature like a leaking water main or a pipe. What was causing these surface water expressions? In fact, in the actual air photo itself, if you would zoom all the way in, on Google Earth, you can actually see the sidewalk is wet from one of these seeps. So this is a persistent feature. The other thing we observed when we were out there is we installed a well on a former raised concrete slab with a 3-foot stick up. And after the well was finished, we noticed that groundwater was actually behaving in artesian conditions and coming up and out of the casing. And so we wanted to know what subsurface feature would cause that. Based on all of our borings, we plotted that the remaining concrete slab and some of the other concrete features that formed a continuous and impermeable surface, in conjunction with the rapid change in topography, that the site is basically a hill that starts at the top of the property and slopes sharply down to the road. And the combination of the change in topography and this confining layer of this concrete basically gave us a potentiometric surface. So it put the groundwater under a pressure to this level of elevation before it went under the slab, and that's why we saw the surface expression of the surface water coming out of the stick-up casing. Same thing with the seeps. We found that the surface water elevation for wells that were on the edge of the concrete slab was very shallow, almost at the surface. So our groundwater is intercepting the surface and causing the groundwater seeps that we were observing. We also mapped the geologic features for the regional. And we noticed that there was a fault that ran through basically along this stretch of road. And it continues all the way through Saratoga, all the way to the north. It's part of the geologic feature that's responsible for the hot springs. And we noticed an offset when we drilled several bedrock wells of approximately 15 feet. And this bedrock offset corresponded with a rapid change in topography. The surface elevation of the road is approximately 15 feet higher than the parcel that's immediately to the southeast of it. And our offset in bedrock matched the expected offset you would see with this fault system. So we were able to put in a bedrock fault within our cross-section to allow us to explain why the bedrock changed in the apparent depth of the surface. So this was one of our more complicated geologic settings. The second example is a site that's it's right near Clifton Park, New York. It's in Half Moon, New York. And the site setting was a former section of the Erie Canal. It was then filled in with municipal waste and some industrial waste in drums throughout the 1950s and 60s, and then covered with a thin layer of fill material and closed, and it's now used as a park. And so we were investigating if the former landfill materials were causing any impacts to receptors or the Mohawk River, which is to the south of this line of section here. The important thing that we observed when we were on the site was there were several flowing culverts that seemed to connect drainage ditches that were on one side of the road directly with the river, and we wanted to know if the depth of the drainage ditches intercepted the landfill material and were potentially introducing contaminants to the Mohawk through a surface water conveyance. Based on the depths that we observed in our borings throughout the site, we have borings on both sides of this feature, but in this area we focused on this specifically because this is where the majority of the culverts that were flowing were observed. The landfill material was below the surface of the drainage ditch, and the analytical data supports that conclusion. There is no difference between the up and down gradient sides of the flowing culverts, and we had pretty consistent groundwater concentrations across the site, so no evidence that the landfill material was increasing or affecting the groundwater quality more than what it was when it was entering the site. This is also an example of how perspective is going to change the order that you're going to display your borings. So from plan view, it goes location number 1, 2, and then 3. But in your line of section, location number 2 is your closest boring to the beginning of your topographic profile. So when you're looking at it from the side view, you're going to have sample location 2 first, and then sample location 1, and then sample location 3. And that's why it appears in that order on this line of section. We also had very limited sampling opportunities in this area of the site. We know that there's a history of buried drums, and we did not want to hit them when we were drilling. And there's no room to drill on the other side of the road. So what we used were aerial photos to show that this entire area was at one point completely filled with water as part of the canal. So it would have a consistent geology, at least during that period. And then the landfilling was done in this section of the site roughly at the same time. So we made an assumption that the lithology would be consistent throughout this area of the site. If we go back and collect additional samples and we find that there's a difference in the lithology in portions of the site that we previously didn't investigate, we'll go back and update the cross-section to reflect those new data points. And then this last real-world cross-section example that was useful, this is a site in Brooklyn, and we had 2 groundwater dissolved phase CVOC plumes. They had different constituents, and they also had radically different flow directions. And what we found when we did a historical review was that there was a 13-foot by 9-foot wide culvert/sewer main underneath the road. It was constructed of arched brick, so it would be a permeable sewer line. And this sewer line intercepts the groundwater. And in a combination of an additional preferential flow path and more groundwater or more water entering the system from the sewer, leaving the sewer, we were able to show that these plumes change direction once they interact with this subsurface feature. So for this particular cross-section, the concentrations, the distribution of contaminants, and subsurface features were the most important questions that we were trying to answer. The geology was of less importance for this particular investigation at this stage. These, in vertical exaggeration, you can see how it stretches the vertical, even though it's only 9 feet tall, it appears taller than it does wide because of the vertical exaggeration of this line of section. So this is an example of kind of an effect of that use of scaling. And then this is the last real world example, and this is what I would determine to be a bad cross-section. This is a site near Albany in Colony, New York, and there's several features with this cross-section that don't give you a lot of confidence that it's an accurate representation of the subsurface. The predominant geology here is a silty sand, but there's these gravel layers that were found in individual borings, but they made no attempt to connect these layers or to see if these layers were significant for the contaminant transport. And these different colors correspond to a concentration gradient of CVOCs in the groundwater, and the concentration gradients don't interact with these layers at all. Typically, your groundwater is going to be affected by higher or lower conductivity layers in a specific way. In this sense, they didn't show that happening. So these layers don't have any added value in the understanding of the contaminant transport. There's other issues with this cross-section, including this entire lobe of contamination that they have in the subsurface was needed to fit their model instead of looking at the data and making a model fit the data. They have a slight detection in this well, and this well was non-detect, and so they had to extend their plume about twice as far as they should have to just touch the bottom screen interval of this well, and it doesn't represent an accurate depiction of the subsurface. And when we sampled the site ourselves, we came to a much different conclusion and also a different remedial strategy.
In their defense, though, Chris, the lines are dashed.
Yes, they did at least dash the lines.
All right, this is an example of not considering really the geologic environment, and in some ways creating the cross section just to fit contaminant data, which also doesn't have a lot of density to it in this particular situation.
Yes, and the more data you can collect, and the more data you can collect in a non-biased positional way. So if you have the opportunity to collect your samples in an evenly spaced grid, if no information is known about the subsurface conditions of the site, that's going to give you the best depiction of the subsurface. If you have a good understanding of where your contamination or your source area is, then biasing your sample locations towards delineating the source area is then more important. So your investigation, and especially the borings that you're going to use to develop your cross sections, should really be tailored to answering a specific question, not just kind of fitting a strange CSM. That
this is also a good example of a very common problem that we see a lot in completed investigations, where the investigation is completely focused on what are the concentrations of the contaminants and where are the concentrations of the contaminants, versus looking at it from a geology perspective and thinking about and understanding what the subsurface is like and how that impacts the contaminant transport. Because you can see what they did here is they have detections, and then they forced the subsurface to sort of match where those detections are. What I like to see, and what I try to do in all of our projects, is let's make the cross section, talk about the geology, talk about what we think is going on from a depositional environment, from a standpoint of is there disturbed layers with fill, before we even get the sample results back from the lab. So we get back from the field, let's lay out the soil borings, and let's talk about the geology and how that's going to impact contaminant flow, and how that's going to basically update our initial conceptual site model that we had for putting the borings where they are. So what's changed, and a key to really being able to take these sites and work into an effective remedial strategy is to understand the geology very thoroughly. A lot of times you get a remedial strategy that, and no offense to the engineers out here, is developed by an engineer and blind to the geology and the flow in the subsurface, the contaminant transport. There are universal laws of gravity and gradient and things like that always happen, but the geology controls all of that. Remedial strategies are considering now the overall energy impact, carbon footprint, things like that. So the idea of taking a big hammer to a small site is very costly and inefficient, both from a monetary and kind of a carbon and energy standpoint. The worst thing you can do is have a remedy that's not going to work. So if you have a subsurface geology that you don't thoroughly understand, and you propose to do some ISCO injection somewhere, and it isn't where the contamination is coming from or going, it's just going to be a complete waste, and it's not going to work. So we need to really understand the geology thoroughly so that we can get right-sized remediation options and really have a good understanding of where things are. And I think I'm gonna make one more point that I know we're going to be bringing up quite a bit as we get into CSMs and even going forward. We started this with the soil boring log, and a lot of times, unfortunately, that is treated as a kind of an entry level. We get somebody out there with limited training, take the boring logs, write down what you see, and it's almost a throwaway, and it shouldn't be, because that is something that we're going to be basing remedial strategies on, that data. So that data has to be good. We have to be thinking about the geologic setting, how the sediments that are there got there, as we're doing these boring logs so that we do have things that make sense and are reflective of the real world conditions as we are moving forward on these projects. I'll get off my soapbox now and let Chris go.
Thank you for joining our talk on cross-sections and how to develop them for conceptual site models. Please let us know if you have any questions or feedback.